Right. So everybody can see, right? Yes. Nice. So today we're going to look at the DC motor tutorial. So we had 5 questions. The first one should be straightforward. That is just straight out of the notes, the description. So I don't think you all should have any problem with that. We will go to the calculation questions. So the first, number 2, the first calculation question, a 30 horsepower, 230 volt, 1150 RPM shunt motor has 4 poles, 4 parallel paths, 882 armature conductors. The armature circuit resistance is 0.17. We have rated speed, rated output. The armature current is 110 amps and the field current is 2.2 amps. And then we have to calculate all of these things: the electromagnetic torque, the flux per pole, the rotational losses, the efficiency, shaft load. And then if the field flux is reduced, determine the new operation speed. So for DC motors, you will realize that the circuit is very simple. We always just have a source and a couple resistances. So we could start off here. So the first thing you want to do all the time is just draw the type of motor that you have. So we have a shunt motor in this case. So we are going to have the terminals, our armature resistance, and the motor. And these things here represent the brushes, in case you're wondering why we draw that there. And this is the armature resistance, right? So the armature resistance is always in series with the motor because obviously this is part of the motor. This represents the windings in the motor. And then we have, separate from that, we have the field, right? Now, sometimes you'll see an inductance included in the field, and also you might see an inductance included in the armature. But these are really for transient studies. In steady state, since this is DC, we assume the inductance is short circuit, which is a pretty good assumption for most cases, right? So in steady state. So we have our armature and field, and we have armature circuit resistance. And just a reminder for everybody to please keep on mute. Unless you have something to ask, then you could unmute and ask, or you could ask it in the chat. So we're just trying to minimize some of the background noise here. Good? All right. So, right, so we have our motor here, and we're given the armature resistance is 0.17 ohms. And the field current is 2.2. Sorry, this is the wrong thing I drew here. This is a separately excited, but a shunt. So here is the shunt motor. And we know this branch here is 2.2 amps. And we are told that at rated, when we apply the rated voltage, we have rated speed, rated output. Armature current is 110 amps, right? The input is 230 volts. And the output is 30 horsepower. Now this output of 30 horsepower represents the power available to the user. So this is after all the losses and everything. This is the amount of power available to the user. And that's a very important thing, because when you buy a motor, you don't want to select a motor based on some internal parameter, and you don't actually know what you're going to get out after the losses and so on. You'll have to do this during for your final project as well. You'll have to calculate typically what is the torque and power of the load that you require for the application, and then you have to select a motor. So you want to see right at the start that the motor can handle the load. So this is different, if you remember, from when we talked about the transformers, because for the transformer, it was a through device. It was just converting power from one side to the next. And there was this confusion about, you know, when they specify the power, which side it is on, because usually they say, well, the rated power, you could get it from any side. So it's supposed to be the same on both sides, but there was that shunt branch in the middle that was taking away some of the power. So it wasn't clear whether it should be input or output, right? And that, but under normal circumstances and the full load, they're pretty much the same. So it was a good approximation, right? But in this case, because you want to spec your motors for the load, you want to know that this is what the output of the motor could give you. So this 30 horsepower is equal to P out, right? So this is something for all your motors that you would have. The horsepower value is the output power. Good. So we are given some other things here, like the armature conductors and so on. And typically what I do for DC motor questions is I just write down the few equations. There are a few equations that we have to know. So I usually just write them all down at the start, right? So this is my MATLAB script for this one. So you'll see we have some of the equations here with all the definitions, and then you basically have these two equations again here that you have to know, right? The torque is K phi by I, and that is something you'd find for all the motors. The torque is related to the current. More current, more torque, right? And for the, or more torque, more current rather. So, and then EA, the armature voltage, is K phi by omega. So that this is related to the speed, because of course, the faster the motor is turning, the greater the rate of change of flux that is going to cut the conductors in the rotor. So the higher the value of the induced EMF in the rotor. Good. So these are the well, this shouldn't be equal to E. There should be another thing here. PE is equal to EAI. So, which is your electric power, your electromagnetic power. Right? So, and apart from that, you just have your normal little circuit analysis that you have to do. Right? That you could get the voltage drops across here and so on. So we have this here is EA, and now we're required to find some different things. So the first thing we require to find is the electromagnetic torque. So we need to find the electromagnetic torque, that is TE is equal to PE on omega. So this is what we know as the equation for the torque. And in order to get the torque, or we could also have that K phi by omega, but we don't have K phi. So, so we need to get PE by omega, and we know PE is equal to EAIA. So that is EAIA over omega, right? So how do we know what omega is? Well, we are given, I believe, the speed was N is equal to 1150 RPM. So we could convert that to omega. Remember, RPM is revolutions per minute, and we want to convert that to radians per second, which is omega. So in converting to radians per second, revolutions per minute to radians per second, one revolution is 2 pi radians. So we multiply by 2 pi, and then we divide by 60 to go from minutes to seconds. So omega is equal to 2 pi n on 60. So we have n, we have I, we don't have EA. So we need to find EA. And EA if we look at it here, we know here is 230 volts. We have the current, we have this resistance. So we know this is going to give us a voltage drop in this direction. So we could find EA as, let me put it here, EA would be equal to VT minus IA by RA, because of course we are dropping the voltage going in that direction. Good, everybody okay so far? Right, so now we have everything for TE. So EA is VT minus IA RA by IA over 2 pi n on 60, right? So if we work that out, let me just bring down this here. Right, oh, this might be better to do. So, right, so we work it out here. EA, we worked it out as 211. PE, we get PE as, let me generate it there. PE is 23.24 kilowatts. And then we we divide PE divided by omega. Omega is what we worked out here. 2 pi by n over 60. And when we work out the torque, we get 193 Newton meters. Good. The next thing we want to get is the flux per pole. So for the flux per pole, we're going to use this equation here, which is this EA is equal to phi NZP over 60A, right? Where we have all of these things here, number of poles. So we have the number of poles, I believe, 4 poles. Number of active conductors is 882. Number of parallel paths, which is A, which is 4 here for the what you call it, type of winding. 4 poles, 4 parallel. Oh no, sorry, they just tell us the number of parallel paths, right? So for lap winding it is P, and wave winding it is 2. So here it is a lap winding and the rotational speed, and that is everything that we need here. So the only thing that we don't have is phi. So we calculated EA just now here, right? So we could just rearrange this formula. So phi is equal to EA by 60 by A on NZP, and that will give us the flux at 0.0125 Weber per pole. Okay. The next thing we want is the rotational losses. So this is one that often gives people some trouble. So the rotational losses, by the way, you all, I'm not sure what sort of devices and so on you're using. The split screen is okay for you, or you prefer to get the whole screen? Split screen, whole screen, anybody? Okay, good. All right. So we have, if anybody is on their phone or anything and they need to do the whole screen, let me know it. Okay. So the next thing we need to do, where is my cursor? Too many monitors. All right. So now we have, let me redraw this here since we're in the smaller screen now. So we have and this was 0.17, 2.2, 110, 230, 8. Good. So next we want to find the rotational losses, right? So this is something that often confuses people about how to get the rotational losses. So you have to think about the power flow in the system. So how is the power going from input to output? So from the input here, when the power comes in, right, what is happening with it? You have the voltage and current that gives you the power. Then you have some power dissipated here in these resistances. Then the rest of the power that makes it to here is the electromagnetic power. The electromagnetic power then is wholly converted into mechanical power, right? So all the electromagnetic power gets converted to mechanical power, but not all the mechanical power is useful power. So some of the mechanical power goes into friction, some goes into moving the mass of the rotor itself, some goes into windage. And the word is windage and not windage. It has nothing to do with windings. It is to do with wind, the air. This is air resistance, right? So it is windage is the word. Right. So some of the mechanical power will be converted into friction and windage. So those are the things that represent the rotational losses. So we want to get now, the losses are then, we have the electromagnetic power here, right? PEM. At the output, at the user side, we have P out. And the losses that take place here are the friction and windage, or the rotational losses, right? You hear them referred to as both. So, right? So what we need to do is get the difference then between the output power and the electromagnetic power. So you'll see here, P rotational is PE, which is your electromagnetic power, minus the output power. Good. So how do we get the electromagnetic power? We have actually calculated it up here somewhere, right? EAIA. So we could use that. The other way is we could find, well, actually, let's just use that PE because we already found it. We could go ahead and get your input power and then minus the losses and so on to get the electromagnetic power, but we already have it, so we wouldn't bother to go down that road. So we have the electromagnetic power, which is 23243. So PE minus P out, and P out is the horsepower. So that is 30 multiplied by 746. And 746 is just the conversion. Horsepower is horsepower to watts is basically the same units of power, right? Just a scaling factor. So you're not really converting to anything different. So when we do that, we get the rotational losses to be 863 watts. Now we want to find, after that, the efficiency. So remember, the efficiency eta is equal to P out on P in. This is essentially what it is, multiplied by 100 in percentage. I noticed a number of people forgot to multiply by 100 in their labs, even though the questions ask for efficiency in percentage, right? So here, I typically just calculate it in as a decimal, but really it is a percentage, right? So, right. So we want P out on P in. We know what P out is, which is the horsepower. Now we want to get P in. So we have P in is the same as P out plus P losses. So we could take it in a number of different ways. So we could say P out plus P losses, and we could get P losses from the rotational losses plus IA squared RA plus the losses in the field. And you'll notice we have no resistance for the field, but we have, because it is a shunt winding, we have the voltage and we have the current. So we have V by I field. So we could do it like that. Or the other way we could do it is we could say the input current, the input power. If I wanted to find P in directly, I could say the input power is equal to V in by I in, and that is equal to V in multiplied by 110 plus 2.2, right? So 110 being the armature current and 2.2 being the field current, 110 and 2.2. So this is 112.2. So these two together will give us our input current, our input power. And then when you do P out on P in, we get an efficiency of 86.7%, right? Good. And lastly, we have the field flux reduced by 15% of the original value by means of a field rheostat. Doesn't really neither here nor there. The important thing is that it is reduced by 15% of the value. Determine the new operation speed. Right. So we have now the field flux reduced. So we want to get the the shaft load, right? Before we get to that one. So the shaft load, I was wondering why I had this calculated here, right? So the shaft load is simply P out on omega. So you see the electromagnetic torque is P electromagnetic on omega. The shaft torque is P out on omega. So this is the torque available to the user. So it is the same as electromagnetic torque, except we subtract the rotational losses. So we had some of that power going to friction and windage. Now we have just the net power output to the shaft. So that is P out on omega, and that works out to be 185.8376 Newton meters. Good. So the next one now, we have the field flux reduced by 15%. So we have the old K phi. So here we are using these two equations, right? So when the flux is reduced, these are the things that are going to be affected here. So we're going to assume that the torque remains constant, because remember, we didn't say anything about the load changing, and this is the torque has to do with the load, right? So assuming you're driving the same load and you just reduce the field flux, what is going to happen? So you have the same load, so the same load torque, and then you reduce this K phi, right, to 0.85 of its original value, then that is going to change the current. So you'll see here we have the new current is equal to the old current divided by 0.85. So this is just IA is equal to T. So this T is equal to K phi. Let me write it down on this side here. So T is equal to K phi old, IA old, which is equal to K phi new, IA new, right? So this remains the same. So if now K phi new is 0.85 of K phi old, right? So then I will have here K phi old, IA old is equal to K phi old by 0.85. So then IA new must be equal to IA old over 0.85, right? For these to cancel out and this to be equal. So IA new, everybody understands that? Now, when you do the, assuming this question is about the percentage sign is about the labs, this is, no, you don't have to put in the percentage sign, you just have to put the answer, right? You don't have to put in units for any of them. You just have to put in the answer. So, right, so we get our new IE, and then since we have the new IE, again, we're going to have the, our circuit here. Right? So we have the same 230 volts. We have IA new. So we could work out EA new here again. So EA new is equal to 230 minus IA new by RA. So we can work out that. Let me just take out all of these things so you could see the values. Right? So the new IA is 129 amps, which is more. And then we get EA new 208 volts. And then the omega new, we are going to use the other equation, which is EA is equal to K phi by omega. So omega is EA on K phi. Right? So omega new is EA new on K phi new. And that works out to be 139.467. Now, if you want to see that, what is that in terms of N? N new is equal to omega new. And how do you think we're going to convert this one? So here we have radians per second. We want to convert to revolutions per minute. So seconds per minute, we multiply by 60. And then radians to revolutions, we divide by 2 pi. Right? So when you're doing MATLAB, you'll see I have two divisions here. This is every time, whatever you put at the right side of the slash will go on the underneath of the, like if you imagine it like an equation like this, right? With multiplication and addition, whatever is behind the asterisk will go on top, and whatever is behind the slash will go below. So this is the same as 60 over 2 pi, right? That is the same as 60 over 2, like that. Good? So if we want to see what that is, now we have 1331. So we went up from 11, what was the original speed? 1150 to now 1330 or so. Right. So the flux is reduced and the speed increases. Good. And you all have seen that in flux weakening to get higher speeds in the motor. Right. So now let us go. Everybody's okay there? Where is the 0.85 from? That is from the question. The field flux is reduced by 15%. So that means 100 minus 15 is 0.85. Right? 100% minus 15% is 85%. Yeah. So, okay. So let's go on to the next one now. Everybody okay with this one? All right. Let us see. Number 3. Where my cursor? Right. Right, number 3. So here we have a separately excited DC motor operated at constant flux has an armature resistance of 1.03 ohms. So again, we're going to just draw our diagram. So we have a separately excited motor this time. Uh, 1.03 operated at no load from a 50 volt supply. And it develops a speed of 2100 RPM and draws a supply current of 1.2 amps. Good. This part of the circuit not that important now. When you're using these separately excited motors, then the only thing this could affect is the flux. It doesn't affect the input current or anything. So, right, so this is what we have now. Determine the numerical value of K phi. So let's see what we're going to do. So we have 2100 RPM. We want to find what is the equivalent in radians per second. So again, because we're going to use this equation here, EA is equal to, I don't know, I guess I copied and pasted from the last one, right? So we're going to use this here, right? We want to find K phi. So the easiest thing for us to do, we can use either one of these equations, but the easier one to use, because the easier thing to get is this voltage rather than working towards the torque. So we're going to use this equation to get K phi. So we have the speed, we just have to work out the EA, right, the armature voltage. So again, same thing, EA is equal to VT minus IA RA, right? So VT minus IA RA, that works out to be 48.76 volts, right? Now we have EA, and we have the RPM, which is 219. So we could work out K phi, and that is just EA on omega, and we get K phi to be 0.2217. Now the rotational, the next thing is the no load rotational losses, right? So how are we going to get the no load rotational losses? Before, what we had was the output power minus the electromagnetic power, but we don't have what the output power is here. It didn't tell us what the horsepower is. So how are we going to get it? So the way we could get it is, or the reason why we could get it is because we have no load on the system. So with no load on the system, all the power goes towards the friction and windage, right? So if you just leave your motor with nothing connected to the shaft, then the load that you're seeing there is actually the rotational losses. That is because the only thing that the motor is turning is the mass of the rotor. It is combating against the friction, which is the friction of the bearings and so on. And it is also combating the friction of the air. So the friction and windage. So the rotational power here is the electromagnetic power, right? So if we look at it with our same equation that we had before, P rotation is equal to P electromagnetic minus P out. For no load, P out is 0. So we get P rotational losses is equal to P EM, right? So the electromagnetic power now we know is EA IA. We have EA, we have IA, which is 1.2, right? So we multiply them together, we get the rotational losses 58.5 watts. Good. The next thing we want to get is the efficiency. So for the efficiency, oh wait, did I miss out something here? No. Right, so efficiency, I didn't calculate the efficiency here, part B, part C? No. All right. Anyway, so for the efficiency, we will have P out on P in. Oh no, wait, I'm looking at the wrong question. That is why. Because the efficiency in this case would be 0 because we have no load. So since it is running, we just have the rotational losses. So the right, electromagnetic torque developed by the motor. So now we have the torque we know is T E, the electromagnetic torque, right? So is K phi by IA. We worked out K phi already. We have IA, so we could use that. Or we could use, if we want, the electromagnetic power over the speed. And we have the speed, so we could do any one of those. So we could say T E is equal to PE on omega, or it is equal to K phi by IA. So we could work out any one of these. We have IA, we worked out K phi already, I believe. Yes, so we could work it out this way, or we have PE, which is in this case the same as P rotation, and we have omega, which we worked out as well. So either way you want to do it, you could do it, and you should get the same thing. So here I use P rotation on omega, and the electromagnetic torque, which is really the friction torque, that is what we would call it here, because it is all from the friction and windage power, is 0.26 Newton meter. Good. So part D, the output power when the motor is operating at 1700 RPM from a 48 volt supply. So now we're changing it a little bit. So we have we have 48 volts now. This is 1.03 and 1700 RPM, right? So now what we're going to assume is that the flux remains the same. Remember, this is, if we had a shunt machine, a shunt excited machine, then it would be the input voltage here would have affected the current, and that will affect the flux. But in this case, it is separately excited, so that doesn't make any difference whatsoever to us. So we have the same flux, and we just have a different speed. So we know EA is equal to K phi by omega. We now have a different speed. This is, to get omega, we have 1700 multiplied by 2 pi on 60. And I have K phi that we worked out before as 0.2217. So I could work out my new EA here, right, which is K phi by omega. And that gives me 39.48 volts. So 39.48 volts, and I could now calculate what my input current is. So I have 48 volts here, 39 volts there. So I could calculate my IA, which is just the difference in voltages over the resistance. So we'll see that here. IA, if I could find my cursor. Here it is. So IA is equal to VT minus EA on RA. So I could calculate that as 8.2728 amps. And then the electromagnetic power is EAIA, right? That gives me the power here. And that power goes into two things. It goes into the friction and windage and the load power. So the output power is now that electromagnetic power, which is now non-zero. And we're going to minus from that the rotational power that we assumed was constant, the rotational losses that we assume is constant, right? So the assumption of constant rotational losses is simple, but it is often used. Obviously, the faster you turn something, the greater the wind resistance would be. So you have more losses like that, and of course, and then you get other things as well as you have heat. The faster you turn the thing, and you have more friction losses in the core, you get more heat. The windings heat up, and there's a whole interconnected process. But for simplicity, often the losses are just taken as constant, right? So again, this is the difference between engineering and mathematics and physics that you'd have done in A levels and so on. In engineering, we work with a lot more uncertainty. So a lot of the things are approximated, and the goal is to balance it such that the approximations and so on don't cause any problems, and the assumptions don't cause any problems in your system, right? So right. So good. So that's it. So we computed the output power. And again, this is the shaft. Once you hear output power, this is equivalent to the horsepower. This is the shaft power that is available to the user, right? So you want to make sure and get your losses out of it. Okay. So let us go now to question 4. This is a short question. Okay, so we have this time a 2-pole separately excited DC generator has full load conditions, 200 volts, 15 kilowatts, 1000 RPM. Find the generated EMF when the conditions are altered such that the flux is reduced by 20% and the speed is doubled. Also find the output power for a current of 50 amps at these new conditions, RA 0.1 ohms. So this time, we have a generator, right? So the current will be going out, IA, PA. And for the generator, just like for the load, we specify things on the output. For the generator, we also specify things on the output. So we would want on the output here, we have 200 volts and 15 kilowatts and 1000 RPM. That is what we should get at the output. So so now we want to find the generated EMF when conditions, and this is, sorry, 0.1 ohms, 0.1, right? So we want to find the conditions. Okay, so we have to change these things up and see what are the new conditions. So the first thing we can figure out here is what is our current. So we have 15 kilowatts, 200 volts. So I can actually calculate my current there quite easily. Just P on V, right? So let me run this here. Let me just rename this. Okay. Right. So Wait, I think I made a mistake there. Anyway, we'll figure it out as we go along. All right.
I think it's supposed to be EA by 0.8 by 2.
By 2. All right. Yeah, it would be related to the, oh, the speed is doubled. Okay, cool. All right, so let's see. So we have IA is P out on VT, so we get 75 amps, right? Now we could work out EA here by, again, we have, this is VT here. Now we have the voltage dropping in the opposite direction. So when we had the, so now EA here will be equal to VT plus IARA. When we had it acting as a motor, you would see it was VT minus IARA, and that is just because of the direction of the current. Okay, so VT plus IARA, so we get EA is 207.5 volts. Now we want to find what is the find the general when the conditions are altered such that the flux is reduced by 20% and the speed is doubled. So if we reduce the flux by 20%, so remember here we have EA is equal to K phi by omega. So I'm doubling the speed, right? So the new EA is equal to K phi by 0.8 by omega by 2, right? So that is your new EA there. And that is 332 volts. And now we want to find the output power for a current of 50 amps at these new conditions. So now we have we have 332 volts. We have an output current of 50 amps. And we want to find the output power, right? So we have VT, and we know P out is equal to VT by IA. We have IA, which is 50. We need to find VT. So we just, again, use our circuit equations. So we say this will drop this way here. So we say VT is equal to EA minus IARA. Let me put that in here. Right, so VT new is equal to EA new minus 50 by RA. And then we have VT, we want to get P out new, and that is equal to VT new multiplied by 50, which is the new let me put it up here so it will be clearer. IA new is equal to 50. So then here, right? So now the new power out, the new terminal voltage is 327, and the new output power is 16,350. So this is probably not a safe way to operate this motor if the rated conditions were 200 volts and 15 kilowatts, right? Of course, you could always operate your motor beyond its ratings, but you can't do so indefinitely, and it will degrade the life of the motor. Same thing for a transformer, for any machine. The reason we have the ratings and so on is these things are tied to the mechanical systems. And I say the mechanical systems, I mean things like what is the clamping pressure on the windings, how much insulation it has, what is the thermal performance of the insulation. So if you operate the motor at a higher, you use it for a higher torque application, you're going to draw more current, your winding is going to heat up. That heat is going to start to damage the insulation. You mightn't see any difference in the motor immediately, but instead of the motor giving you 20 years life, it might give you 15 years life or 10 years life. So looking at these sorts of things and monitoring the equipment, and so this is a big thing in industry now. So this is called condition-based monitoring. You might have heard people talk about condition-based monitoring and asset management and so on. So there are huge fields of study to figure out how you could operate your equipment most effectively given the timelines that you might have. So you may have some motor that is aging, and you might have new technology coming out, and you want to replace the, you might see, okay, it might be beneficial for you to replace your motors. When is the best time to make that change? What is the most economical time? So you could probably, you know, overload the motors a little bit more, pick up some extra load, or if you need to. Well, this is more, well, actually that works more for, that analogy works more for the situation works more for like the generators and the power system. You have to bring on additional or transformers. You have the load growing. When do you put in a new transformer? Well, you can overload this one for a particular time before you change it. It will shorten the life. But if the load is growing quickly, you might have to change it anyway. So these are the kinds of things that engineers will try to balance and try to figure out when is the best time to make these changes. So that's a huge, huge field of study. And of course, it is millions and millions of dollars you're talking about in doing that, right? So something for you all to look at in case you're interested in that sort of thing. Right. So the next one, last question, we have a 400-volt shunt motor. Let me pull up that last one now. Right, so a 400-volt shunt motor. 15 horsepower, normal full load speed of 1200 RPM. Armature current at rated speed and full load is 32 amps. Armature resistance 0.7. Okay, so we have a shunt motor here. .400 volts DC. 15 horsepower, 1200 RPM. Armature current at rated speed and full load is 32 amps. And remember, the armature current is always the current directly into the armature resistance. It is not the input current here, right? That will be the same in some cases, like if it is a series motor or if it is a separately excited. But if it is a shunt, then it will not be the same because you have this IF down here as well, right? So field resistance 200 ohms, armature resistance 0.7 ohms. And we want to find the rotational losses for the machine. So rotational losses again is PE minus P out. We have P out, 15 horsepower. We need to find PE. To find PE, we need to find, so we have P rotational losses is equal to P EM minus P out. That is equal to EA IA minus 15 by 746, which is our conversion. We have IA, right? We know IA, which is our 32 amps, and now we need to find EA. And again, we have the voltage, we have the current, we have the resistance. So it's a simple series circuit. So we can say EA is VT minus IARA multiplied by IA minus 15 by 746, right? So we have all of these things here. We have VT, we have IA, we have RA. So we can work this out, and you'll see here we work it out to 893.2 watts. Good. The next part, armature current of 16 amps, determine the speed, the output, the power output, and the useful torque. Okay, so the first thing we're going to do is we're going to figure out, based on the last one, what is the motor constant? That is, what is the K phi, right? So K phi, EA on omega, let me put this here, right? So EA on omega and IA is, so we have omega from before, we have EA from here that when we calculated it. So we could work out K phi, and now we have IA, a new IA of 16 amps. So we want to figure out what is the new speed. So the new speed, again, we know EA is equal to K phi by omega, right? We worked out what K phi was. We want to find omega. Omega is EA on K phi. We need to find EA. EA is VT minus IARA. Good. So we have all of these things again. We have VT, we have IA, we have RA, we have K phi that we just worked out. So we could work out the new value of omega, which is 129 radians per second. And then we could convert that to our RPM, which is multiply by 60 to get to radians per minute, and then divide by 2 pi to get to revolutions per minute, right? So that works out to be 1235 RPM, right? That is up from 1200 RPM, was it? Yes, up from 1200 RPM. Power output, so we know P out is EAIA minus P rotation. So we have EA that we just worked out here, right? So we have EA, we have IA, which we were given, and we have to get the rotational losses. And again, we assume the rotational losses are constant. So we have the rotational losses that we worked out here. So P out is EAIA minus the rotational losses, and that gives us, that is 5.3 or so kilowatts. Good. Lastly, the useful torque, right, which is the same as the useful torque, the shaft torque, the output torque. All of these things mean the same thing, right? So you'll have a few different names for this. People will call it shaft torque, useful torque, output torque or so. So what you have to remember is that is different from the electromagnetic torque. The electromagnetic torque is the one developed inside the machine, and then the useful torque or net torque, you might hear it as well. All these are names for what the torque available to the user is, right? So that again is P out on omega, and that works out to 41 Newton meters. And that, I believe, is the end. Good. Any questions? So how you all felt this tutorial? Easy? Normally the DC motor question is the place that everybody makes full marks, because as you can see, it's just simple, a simple one resistor DC circuit for the most part. Okay, so if no questions, that is it. We'll see if your induction motors things should be up this week. I will see if we will have class next week, or you could get 2 weeks to do the tutorial, like the last time when we had the last week free. Usually Andrew would do the lab session next week, but since he's put it up online, there's really no need for him to do that. So I'll let you know during the course of the week whether we'll have class or not, or maybe you could let me know depending on how your tutorial is going, right? When you have the induction motor tutorial. Okay. All right, well, that is it. There seems to be no questions. Last call. Going once, going twice. Okay, well, that's it. I'll see you all either next week or the week after.